both kinds of information about children's behaviour are essential, and the two kinds of information complement each other, in my view, rather well. So selecting one of the two methods is not on the whole a matter of one's preference for doing things in a particular way, but depends on what kind of information you want to get.
The information we get from observations can lead to a theory, and the theory makes a prediction that if we change something, then something else will change also. An experiment arranges the change and allows us to check whether our prediction is correct.
Before we ask you some more questions about the slopes.
To see how it all works in practice, we visited Balfron School near Loch Lomond, where Christine Howe and her colleagues from Strathclyde University have been doing experiments on social interaction and cognitive development.
Do you think they'd both go to the same distance, or do you think one would roll further than the other?
I think one would roll further than the other.
And which one do you think would go further?
The heavier car.
Right. Now, why do you think that?
Because it's heavier.
The Swiss psychologist Jean Piaget argued that, as with preschool children, social interaction promotes cognitive development. And this was Dr. Howe's starting point.
The theoretical underpinnings of the experiments are essentially Piagetian, and in particular Piaget's emphasis on conflict as the mechanism of cognitive development, conceptual change. Conflict stimulated by peer interaction between children. One child experiences a different idea from their own ideas, and through that experience they both hopefully change.
This theory led to a prediction about children working together, which could be tested experimentally.
It seemed to follow from the Piagetian theory that if conceptual conflict is important, and if conceptual conflict can be stimulated by peer interaction, then there ought to be some advantage in having children work with children who had ideas that differed from themselves. That we made the hypothesis that interaction between children with differing ideas would lead to greater change than interaction between children with similar ideas. Do you see this tank?
Yes.
The water in it. That's just ordinary water out of the...
One of the experiments used to test the hypothesis involved children's ideas about flotation. First, it was necessary to find out what ideas each child already had about flotation. This was called the pre-test.
The first one's the bottle. What do you think it would do? Would it float or would it sink?
I think it would sink.
It would sink. Why do you think it would sink, Emma?
Because it's made of glass and it's quite heavy.
Right. We noted down everything they said while they were being pre-tested, and then afterwards we scored their pre-test responses on a 5-point scale. We gave them very low scores if they said things like a ball floats because it wants to. There's no mention of any physical factor involved. We'll give them a score of 2, a middle sort of score, if they mentioned things that were partially relevant, like weight. A key will sink because it's heavy. We gave them a very good score, a score of 3 or 4, if they had some appreciation of the weight of object to weight of water relation. This metal dish. Suppose we just put it in the tank like that. What do you think it will do? That won't float. It'll sink. Why do you think it will sink, Ewan?
Well, it wouldn't be able to, like, sit in the water properly and it will topple over.
On the basis of their understandings in the pre-test, the children were allocated to groups of 4. There were 2 kinds of groups. One kind where they all had differing ideas about flotation, and another kind where they all had similar ideas. The groups which had differing ideas were called the experimental groups, and those where the children had similar ideas were the control groups. All the groups were given a series of tasks which encouraged them to predict whether an object would float and to record their predictions on cards.
So, first thing then is the key. Do you think the key will float or sink in the tank of water?
It's important that the children tackle this on their own at first.
To the bottom of the pile, and we'll go on to the next one. And the next one is the red ring.
They then have to declare their predictions and through group discussion try to come to a consensus.
I thought it would sink as well. I thought it would float because rubber quite often floats and it's not too heavy. It's used for like
swimming rings.
Buoys and things.
But that's solid, is it not?
Yeah. I think it's still quite heavy even though it's rubber.
If you bring a group of children together and ask them to talk about floating and sinking and work out why some things float and other things sink, you'll find that one dominant child immediately takes over and the other children will defer to that child's views. If they've written things down on cards, then they can't hide behind the dominant child. They've got a position which they've got to defend.
When and only when they all agree, they can test their prediction.
I think it's something because of its weight.
Yeah, because it was solid.
Yeah. It wasn't, there was no air inside it.
Yeah, I
Fold
thought
it up and it's heavy.
I thought it would sink because it was heavy and it had a hole in the middle so the water can easily get around it and it would sink. I thought it would because it wasn't hollow. I think it did it because it wasn't hollow and also the water can go through the hole and more water can get around it.
So that's just
5 weeks later, the children were retested using different objects to see whether the predicted change had taken place.
What if it was bigger or squarer, it would probably float. But because it's sort of long and thin, it probably won't.
Right, let's talk about washing up this time. We scored the post-test in exactly the same way as the pre-test, and we simply took the pre-test score away from the post-test score as a measure of change. And change was greater if the children had been in the differing groups than if they'd been in the similar groups.
So the predicted change was confirmed. The children in the groups which had a variety of ideas to begin with progressed more than those who were in groups with similar ideas. Does this mean we can accept the results? Unfortunately, no. There are many possible sources of error in experiments, and critics always have to look for these. Let's go back a little and see how Dr. Howe and her colleagues dealt with those that they were aware of. The first possible problem is that the experimental and control groups might have been different in other unintended ways, and those might have produced the difference in post-test scores.
There's no doubt that the children did vary in a large number of ways. They varied in their age. We had children as young as 8 and children as old as 12. They varied in sex. We had some groups that were all boys, some groups that were all girls, and all the possible combinations in between that as well. They varied, no doubt, in how much they liked each other, how much they liked school, how much they liked physics, and probably, almost certainly, of course, in their general level of intelligence. Now, we've no reason to think that any one of these factors co-varied with difference and similarity. And in some cases, we know that it didn't co-vary because we checked.
Okay, do you think that will float?
Another problem to watch out for was experimenter bias. It was important that the experiment was explained to the children by someone with no knowledge of the pre-test results.
Working closely with the children, there's of course a danger that prior knowledge about children's ideas could actually influence the way in which one behaved in terms of drawing out their particular ideas. In practice, this actually tended to work pretty well. I found that I had little idea what kind of group I was dealing with.
What about the tasks themselves? Some might argue that they're artificial and not related to the real world.
The interactions were not uncomfortable for the children, quite the opposite. The children enjoyed them. In some ways, you could almost argue that the interactions the children had with our tasks were superior to what they have in the normal classroom. There's a lot of research on peer interaction in classroom context. where the results show that a huge proportion of the exchanges are not related to the task, and when they are related to the task, then they're not very helpful. We don't find that at all. We find virtually all the conversations on task, and it's very relevant. So, you know, you might say it's artificial in that it's not what they normally experience, but it's maybe artificial and better.
We generally need as much precision in experiments as we do in observational methods. This also means that we have to ensure that the procedures and tests are reliable, just as was the case with observational studies.
We gave a 25% sample of our pre- and post-tests to 2 scorers who worked with them completely independently, giving them scores. Then we compared the scores to look at the percentage agreement and found that for both the pre and post tests it was well over 90%.
Even if we can satisfy critics that the results of this experiment are valid, we can't necessarily claim that they can be generalized to other tasks or domains. The flotation experiments were in fact one of a series which tested the theory across a range of tasks. In this experiment, children are predicting how far a car will travel after running down various inclined planes.
Try to agree why the car stopped where it did. Make sure that everybody in your group says what they think.
We got it wrong about the weight pushing it forward or something.
And it's maybe the weight went further.
Because it's not got the heaviness to slow it down.
Some cars are heavier than others, and both the slope of the track and the starting point can be varied. The procedure is much the same as the flotation experiment, with pre- and post-tests, similar and differing groups. The results lend even more support for the theory that cognitive development will be accelerated in the differing groups.
Our studies with the primary school children seem to me to give a very strong support for the Piagetian model of cognitive change. They suggest that children do learn from interaction under conditions of conceptual conflict. Moreover, they also suggest that the children need time to work through the implications of that conflict individually.
Although the theory was confirmed, there's still a danger of drawing hard and fast implications from inevitably artificial experiments.
It's wrong to base a causal hypothesis just on experimental methods because of the danger of the artificiality of experimental methods. But what's important here, it seems to me, is that the 2 methods, experimental methods on the one hand, observational correlational methods on the other hand, are complementary. They both have gaps, but in fact they each fill the gap left by the other methods. The experimental methods are good tests of causes, but run the danger of artificiality. The observational correlation methods tell us what actually happens and therefore are not in any way artificial, but on their own don't test the causal hypothesis. So together they make a formidable team. And my view is that you can only have a proper test of a causal hypothesis by combining both methods.
So the research continues, reaching conclusions more by successive approximations than a sudden revelation of the truth. But any observational or experimental study can only be as good as the ideas that go into it. And although research methods can be an aid to social and political judgment, they can rarely make that judgment for us. That depends on values as well as science.